Hi everyone. Today we'll begin a discussion on completely new chapter called energy method. In this chapter, we'll discuss about how we can obtain the deflection or deformation of structures under external loading using the energy method. Okay. Before we begin, let me give you a review of previous class, and let me also give you the review of entire course of flow before beginning today's lecture. So in previous lecture, we discussed about so-called superposition method. We have already discussed about superposition method in the context of solving statically indeterminate problems back in chapter 2 and chapter 3. So because we skipped the discussion on beam deflection under moment and the shear, so we discussed about beam deflection, and we also as a follow-up, we also talk about statically indeterminate problem, because a statically indeterminate problem cannot be solved by assuming rigid structure or rigid material. We have to use the concept of a deflection or deformation and use a deformation or deflection condition as an additional equation to solve for additional unknowns. And one of the example that I can show you today is this is a problem that we discussed in previous lecture. So let's think about a cantilever beam with redundant simply supported end. So without this simple support, we can still satisfy mechanical equilibrium. However, by adding this additional redundant support, we got some trouble. We have the trouble that we have three unknown reactions: one moment, two forces. However, the number of mechanical equilibrium equation that we can bring up is only two: force equilibrium along vertical direction and moment equilibrium. So here, one of the method to handle this problem is, in addition to double integration and quadrilateral integration method, we can use the method of superposition, where we can rely we can utilize the solution for known simpler problem. So we can decompose the problem into two problems, and by considering that problem A and problem B will have different deflections, and deflection condition of problem A and problem B, if we sum them up, they should be equal to the original problem, which implies that there is third constraint: the deflection of problem A plus deflection of problem B should be summed up to be 0 at the end, which is the B point. Okay, so by considering these three equations, and realizing that there is only three unknowns, we can solve for FA, FB, and MA. And after identifying FA, FB, MA value, we can obtain the beam deflection solutions. Okay, so this is the superposition method for beam deflection problems. So today we'll begin a new chapter called energy method. Before we begin, let me give you the overview of entire course of flow. So as I told you, this course have overall two goals. First goal is predict the failure, and second goal is the predict the deformation. So in in the first goal, predict failure, it's over in chapter 8. And what we have done was, we obtained the maximum shear stress and maximum normal stress, and compare those maximum stresses with the material property or design criterion, allowable stress in shear or normal directions. So the flow was this. We begin from the statics in chapter 1. We discussed about like a one by one, like how we can obtain the reactions N, V, T, M, and out of these reactions we can have either normal stress or shear stress. This is the how we can obtain the normal or shear stress out of force or moment. After obtaining these normal stress and shear stress, we need some tools to do coordinate transform and combining normal and shear stress in originating from different forces and moment, which is called stress strain transformation. And because the general 3D stress strain transformation is beyond the scope of this course, we learned so-called Morse circle method to visually memorize the stress and strain transformation formula. After we learn the Mohr circle concept, we solved quite complex mixed loading problems to obtain maximum shear stress and maximum normal stress, and we handled this several of these problems in chapter 8 lectures. Okay, so with this we finalized the lectures on first goal, predict the failure, and then we started to discuss about second goal again, which is the predict deformation. So regarding the deformation prediction, we briefly touched this topic in chapter 2 and chapter 3, where we considered the displacement under axial loading and twist angle under torsion loading. So this is equation from chapter 2 and equation from chapter 3. So in previous chapter 9, we discussed about how beam bending under different forces and moment will cause different elastic curve, and we also learn about so-called Euler-Bernoulli equation. Okay, so Euler-Bernoulli equation somehow ignores this guy, the effect of the shear stress, and considers only normal stress, and based on that we were able to obtain the elastic curve out of this beam bending structures. Okay, so in this chapter, which is the energy method chapter, what you're gonna do is following. So we're gonna do something similar that we have done back in freshman physics. So back in freshman physics, we also learned that displacement can be obtained from partial differentiation of some potential energy. So the potential energy in our course of Me231 will be strain energy. Okay, so out of the partial differentiation of strain energy, we will be able to obtain the deflection. In addition to that, we'll also learn about the the kinetic energy and potential energy method. Back in freshman physics, we learn about like the kinetic energy converted to potential energy, and we can obtain the maximum deflection of the spring. So we're gonna do same thing here. Out of this gravitational potential energy, it will be converted to kinetic energy, and this kinetic energy will converted to deflection strain energy of the beam. Okay, so these are the logical flow on the energy conservation method in Me231. Okay, so with this, we'll be finalizing the entire course Me231, and because this is the last chapter, and which somehow summarizing the entire concepts, please please also study this chapter in detail, because what you're gonna see is that you're gonna have completely different perspective and completely new approach on problem solving, and it will give you another way of to approach solid mechanics and dynamics problems in your later life as a mechanical engineer. Okay, okay, so with this let me stop video recording for this one, and in the next video let me give you the introduction about today's topic and start the lectures for today.